Thanks, Oscar, and yeah, thanks for the opportunity to come to this inspired location. I will briefly introduce you to HiGHS. It's increasingly unnecessary. The name comes from the initials of the original contributors. That's me, Yvette, who's over there, and Huangfu Qi and Lucas Shork, who have gone on to who were Edinburgh PhD students in continuous optimization, who've gone on to big things in the commercial software industry. So we basically solve all the linear optimization problems. So that's LP, QP, and MIP, but not MIQP. And it's available on open source on GitHub, and that's about it. The four things I want to talk to you about which are new. We have a new interior point solver in version 12, and we have enhancements to our MIP solver in the latest version of HiGHS, and two things which are work in progress: enhanced irreducible infeasibility system, or whatever it's actually stands for, HiGHS, and our new first order solver. However, before that, I will just acknowledge JuMP. The relationship between HiGHS and JuMP, as Oscar said, goes back quite a long time. I first met Oscar at a CoinOR workshop in Minneapolis in 2018, where CoinOR was trying to decide, well, how do we go forward from here, and how do we make reinvigorate CoinOR? And two things came out of that meeting. One was that there was a gap in the market for just the LP solvers that we had, and so therefore HiGHS was created. And also I realized that Oscar was young and smart and good person to deal with. Sorry?
Don't give me too much credit.
And I think the JuMP interest began when I presented at Informs in 2019, and Oscar suddenly said, I can stop worrying about trying to make CBC and CLP work every time John Forrest makes some minor tweak to it, which just blows things out of the water, and that at least in the person of Yvette, we've got someone young and agile behind HiGHS who will give, and we've got good performance. And the JuMP HiGHS interface, the Julia interface to HiGHS, was developed by Oscar and Yvette a year later, and HiGHS has appeared as the default solver in documentation of JuMP for a number of years. JuMP also maintains the HiGHS binaries. I should say, we had lots of great advice from Oscar in the early days when we were getting going about how to do things, and the things we couldn't do, Oscar did some of them for us. So that's where the HiGHS binaries being hosted by JuMP has come. And we also eventually did something about documentation, and we chose documenter.jl, and Oscar guided us through the start of that. And well, the documentation is still not great, but some bits of it, like the C API, are nicely documented through documenter.jl. And finally, bring things up to date, funded by Breakthrough Energy. There's a JuMP and HiGHS project working together to improve the open source energy systems ecosystem from the modeling down to the solving. So our new interior point solver is Hypo. We already have an interior point solver that's called IPX. That's the one that was written by Lucas Shork in his PhD with Jacek Gonzio. And unlike virtually every interior point solver, it solves the necessary linear systems iteratively with preconditioned conjugate gradient, and it's a general preconditioner which works pretty well for any LP. And as a consequence, because it doesn't have the downsides of most of the open source interior point solvers, it performs best as an interior point on the Mittelman benchmarks. However, it's serial, and there's still a big gap to the commercial solvers, and it's also slightly hard to predict how expensive it's going to be to run, unlike something based on direct factorization. And it also doesn't generalize to QP. It can only solve LPs. So HiPo, we got funding from Google, thanks to energy systems people like Max Parsons and Jesse Jenkins and Tom Brown. And using that funding, Filippo Zanetti has spent 2 years writing this from scratch because we have the MIT license and there was no appropriate, even with any license, any Cholesky decomposition code that we could use. So he wrote it from scratch. And it's been available for a couple of months in HiGHS. And it's available if you're building from source and if you're using JuMP. So at the moment, we have a Python interface which you can't use to get access to HiPo, but you can if you're using JuMP. And so Yvette is working hard on the Python build and has already made great progress towards that. So a little bit of technical details. It's a traditional interior point solver. It forms the LDL transpose decomposition of either the augmented system, and if you know your interior point background, you know where that comes from. The matrix theta is diagonal, and it's got a horrendous range of values from very, very small to very, very large, and that 1-1 block can be eliminated, and that gives you the normal equations, which is the Newton system, also known as. And to factorize that, we use METIS to produce a fill-reducing ordering of the rows and columns, symmetric ordering, which does introduce a dependency into HiGHS. We've been proud, it's not proud, that's true, and also pragmatically, we've really tried to avoid having external dependencies and write every line of code ourselves. But we couldn't rewrite METIS, although we do think it might be a nice idea. But fortunately, METIS is available via a license which is compatible with MIT, and so we're using METIS to get that ordering. And the best way of mitigating the dependency in the build is work in progress. We are learning a lot from seeing people use it and finding out which is the best version of METIS, and people like Alexia have been very helpful in that. Basically, given the ordering, it factorizes the matrix. It's a multi-frontal approach, and so there's parallel processing according to the elimination tree, and that ends up with having to do factorization of frontal matrices which are dense, and so there's parallelism in the factorization. Whether you use the augmented system or the Newton system depends on your problem, and we can do either, and we will attempt to judge which is the best one. The Newton system, which is the lower one, can have an awful lot more structure to exploit and therefore parallel. However, it can have so much structure that it's a full matrix, in which case it's not a practical proposition to factorize it if the problem is of any size. So then you would solve the augmented system. Similarly, if you're solving a QP, then the augmented system in its 1-1 block is minus theta inverse plus Q, and the elimination of that 1-1 block then is horrendous and almost certainly going to be a bad idea. So therefore you want to pivot according to the augmented system, not the Newton system. And then at the bottom end, we need a good BLAS library, and it's been a learning process for us to see what BLAS libraries people have got, and also making sure that people are using the best possible BLAS. So I say it's broken new ground for us. Performance, well, performance is a kind of work in progress in that the code is getting better steadily as Filippo learns from people's use of it. This is some results which Filippo got for some PIPESA models, so that's energy systems modeling, even if it's Python. And you can see there with compares our old interior point solver with the new one, and for small problems the new solver is less efficient. The old solver is definitely better. However, as problem size gets big, the power of the direct solver takes over, and for the that is going to get better. The MIP solver. Well, the MIP solver is quite a different matter. Those are some results I took from Hans Mittelmann's most recent benchmarks, where everything in blue is open source, everything in red is closed source. So currently I just put in one of the closed source solvers, which is the best now that Gorobi's dropped out, and that's Cardinal's COPT. Just for context, so HiGHS is way behind COPT in terms of speed and also the number of the problems which are solved. So the speeds are normalized so that the fastest solver is speed 1. SCIP-C is SCIP, which is the MIP solver from the Zuse Institute, but with Cplex to solve the LPs. So it's not open source. We're meaningfully ahead of them. Vanilla SCIP, which uses Zoplex to solve the LPs, is now quite a long way behind us, as is CBC. CBC and GLPK, those results are really old results. Basically, Hans has given up benchmarking them because they're too slow. And the other solver I've listed is QOPT, which is NVIDIA's MIP solver. Now, Miles said that there's a lot of excitement generated particularly by NVIDIA about GPU in accelerated optimization. And they have got a first-order solver, which is like all first-order solvers. It's going to run very fast on a GPU for what it does, and it's as good as anything else. However, they also have a MIP solver, but what they call a solver, but it's really only a primal heuristic generator. And if you're solving vehicle routing problems, I think it is apparently very, very good. If you're solving general MIPS and you want a provable optimal solution, then it will take a very long time. I've not seen it benchmarked on the MIPLib set, probably because it would just time out on most of the problems. So where it lies in that list, I don't know. But don't think that because it's NVIDIA, it's a fantastically good MIP solver, because it isn't. So that's where we stand, and we're not happy with that because people in the open source energy systems community in particular want a better MIP solver. So our solver was written by Leona Gottwald, who was at Zib, then came to us for 2 years, then went to FICO and is now working for Hexaly. And her solver has basically been the world's best open source MIP solver since 2021. And one particularly prominent use of it is within MathWorks. If you solve a MIP in MATLAB, if you really want to use MATLAB, some people still do, then you will be using our solvers. They ditched what they had in the past about 18 months ago and switched to our solvers. And that's important in the story I'm telling you. However, there's really been very little performance improvement since Leona left us in 2022. And that's mainly because there is no MIP expertise in the HiGHS team. And the one thing, my background is continuous optimization. Edinburgh's strength is continuous optimization. The one thing I've realized from this is that solving MIPS is so completely different. Being a good, experienced, continuous optimization developer really doesn't help that much for a lot of what goes on in MIP solvers. So we're looking to build a team. Now, the team we've got, Franz Wesselmann is employed by MathWorks, and he was maintaining and supporting their old solver. And then when they ditched that, basically he's doing a lot of work for us. There's no money changing hands. He just helps on the HiGHS solver. Mark Turner did his PhD at the Zuse Institute in Berlin and has been funded by Breakthrough Energy money for 2 years as a developer. And I've got PhD student Ben Champion, who is funded by a UK energy tech company, who's also working on MIP. There are no shortcuts to major performance improvement because the MIP solver is inherently so good to start with. Okay, we're still well behind the commercial solvers. That's because MIP solvers are hugely complex and things with lots and lots of tricks in them. So we looked at parallel tree search. As promised by Leona, it was written with parallelism in mind, but it's not as oven ready as we thought, and it really needs MIP expertise to implement it properly. We tried racing the MIP solver with different random seeds and to see whether you could gain advantage that way, and it was fun for a little while, but basically it's non-deterministic and a really horrible thing, so we've ditched that. And I also got some performance by pre-solving analytic center calculation, until I found out that actually that's a terribly bad idea if you're doing that in the middle of a MIP solver, because it implies integrality on variables which can't be fixed. But so finally, the enhancements we've got. Well, Franz is looking at fixing pre-solve bugs and adding things to pre-solve, as well as helping with the general MIP enhancements. Mark has added flow cover cuts and is working on the parallel tree search at the moment. And Ben Champion he's added the feasibility jump primal heuristic, and his PhD seems to be moving towards looking at primal heuristics, and so he's going to contribute that way. Irreducible infeasible system, HiGHS facility. The story behind that is that I started work on it last year, and the mathematician that I am, I was aiming for a provable, irreducible, infeasible system. And I soon realized that it needed enhancements to the primal simplex solver in HiGHS in order to get better performance and get more reliability. And I got busy doing other things. Thanks to talking to people like Joachim, I kind of realized that something very, very simple and crude may well actually be very helpful. And in fact, more generally, for me, I know as a mathematician, LPs can be and LPs and MIPS can be infeasible, and I just say, well, that's a modeling error. Go away and sort it out. But in fact, if you're going to go away and sort it out, solver developers can help enormously by giving information back, and that's what these HiGHSs are all about. So I produced HiGHS Lite, which is a trivial piece of coding, but it just looks for incompatible bounds, and if you work out the upper and lower bounds on row activities in the constraints, you can spot constraints that could never be satisfied, and that could still prompt somebody to say, ha, I've got a mistake here. And it's cheap and cheerful. So that's already in HiGHS. In the last couple of weeks, I've added an option to just find an infeasible system, which is the first part of the process of finding an irreducible infeasible system, and that on its own could still be useful to people. What's coming is extension to MIP. Now, finding irreducible infeasible systems in MIPS is very expensive, very much more so than in LPs. So the plan is that someone will give a sort of budget of time, and basically when that time's out, it will return the best that it's got, even if it's not actually an irreducible system. It's going to be as small as it's got in that time. There's still plenty of scope for performance enhancement, both in the subsystem solves, particularly for LP, and also the bells and whistles you can add. And MathWorks wants that, and they've got somebody who's going to be working on that with me probably in the new year. So hopefully in 12 months' time we should have a very much better facility within HiGHS for HiGHS detection. And so the last thing to talk about is HiPDLP, which is our new first order solver. If you're not aware of PDLP, it's hybrid. It's primal dual hybrid gradient for LP, which is shortened to PDLP. It runs on GPUs, and we've had QPDLP-C, which is an open source MIT code within HiGHS for the last couple of years, and it's been running on GPUs since March. So why do we want to develop one? Well, it's a very active area of research. Even though I've got some cynicism about these first order methods, it's still exciting that we have a third way of solving LPs, particularly giant ones. So there's all sorts of research that's happening, and we want to be able to incorporate that. There's even complete new algorithms, and there's more new solvers around to learn from that are open source. And we just want one within HiGHS. We've got a contract with NESO, which is a UK energy system operator. to develop one, and that will be a kind of test bed for Yanyu Zhu, PhD student of mine, who is funded by the Google money to do research. She's re-implemented QPDL-PC in C++ as the first stage of that, and has started the CUDA implementation. So that's work in progress, and we've got until the end of February to finish that. So in summarise, that's a picture of the Edinburgh-based team. Mark is still living in Berlin. We've developed a much better interior point solver than we had before. We built a MIP team and are enhancing the solver. The IIS facility is being enhanced at the moment, and we are adding a PDLP solver. Thank you.